just to recap what we are doing here, we have the agent, we have the environment. So the environment could be anything. In this example, this was tic-tac-toe, right? So what I do, I am the agent. I am going to act. My action is going to be which cell I'm going to, which cell I am going to play. And then the environment is the collection of the game rule, and the opponent who is playing the game with me. So that is the environment, and the state is eventually what we have on the board when we are playing. So we talk about this particular case. So we say, like, you can call we can number the cells on the game board, so 0 to 8. And then each time that we play, each time that we act, we are just doing one particular action, which is just choosing one of the cells for us, right? And then the state of the game is going to be basically the cells that have been played. Anything left is going to be left as possible choice of the action, right? So we had this particular example here. So we have played both with the opponent. We have played 0, 2, 3, 4, 5. And then the agent decides to play 6. So the state is actually whatever had been played before. So it's going to be 0, 2, 3, 4, 5. And then the action that the agent does is eventually this action 6. So it's going to play cell 6. So the next state, what's going to be the next state? The next state is going to be whatever we have played already, the action of the agent, and the action of the opponent after that, right? So say the opponent is going to play the cell next, so cell 7, then the state st plus 1. After you do your action, the new state is going to be this guy, right? And then the key point here is that whatever the next state is, this can be always written as the previous state, union with your action, the agent action, and the action of the opponent, right? So it means that the next state is only given or only depending on your current state. You don't really need to know what was the very first state, right? So here, this is a state-dependent problem. We talked about the transition and rewarding functions. So the transition function was potentially a random function, which was describing if you are in one particular state, say state st, and then you play action at, what's going to be the next state, right? So in this particular case, you look at this board, and the state that you are playing is all of those, other marks. The red mark is going to be the action. Now, the next state could be anything of this form, like everybody here plus either cell 1 or cell 7 or cell 8, right? Any of them could be the next state, and it totally depends on the action of the opponent, right? So you could say that the transition from st to the next state is going to be of this form, this probabilistic form, right? With some chance it's going to go 1. It depends on the chance of opponent playing 1. It's going to be this one with some other chance, which is depending on the action, the chance of opponent playing 7 and so, right? So this was the transition function. We also had the rewarding function. So the rewarding function is again potentially a random function, looking at your state and your action, and that is going to give you a reward, right? So here in this particular one, this is pretty standard, but you can again say that this is random because it depends on the action of the other side as well. But say that you act at, and once you act at, you're going to either win or lose, or you keep playing. And for each of them, you can just put one particular reward, right? +1 if you win, -1 if you lose, 0 if nothing happens, right? So again, this is a transform function. It depends, it's the rewarding function. It depends on the rules of the game, and of course, in some situation, the move of the opponent, right? Everybody's cool? Everybody recaps what we did last time? So now, you can extend this framework to many other problems, right? One famous example is this cartwheel problem. So this is one of the very famous problems in RL. So what is the problem? You have this hanging pole on top of one cart, and then you have this option that you either push cart right or left, right? Now, you are going to keep getting rewards if you, when you push, that hanging pole is not getting far away from the central line, from the vertical line, with angle more than theta, and your cart is not moving from the center point with a distance more than x. Like if I can keep it very close, like I play like this, right? Left, right, left, right. So this pole is just not dropping, right? So it's just varying around the central line, right? And the cart itself is not getting far away, right? So it's just around the central point. I keep gaining, right? But once it just happens that the pole just goes down or the cart is just moving far away, then you're going to lose, right? And this is a physical problem, right? There is no random or inside this. If you think of physical dynamics, right? But it's hard to describe it in formulas, right? Because you need to really know what is the force that you're using here and what is the friction of that surface and so many other physical things, right? We don't know them, but if hypothetically we know it, then we could compute, right? We could deterministically evaluate the way that we can always gain something, right? So this is, again, the same kind of problem. So for this problem, the agent is the guy who is playing, who is trying to avoid the pole falling, right? And the action that it can do is just +1, -1, right? You can either push right or left, right? This is the actions that you have. And then the environment is essentially the cart pole, right? The cart itself and the pole hanging on top of it. And the physical rules are, again, part of the environment, right? And this environment can be described with one particular state, right? What is this state? Like if you think about the high school physics problem, then you have this cart pole and somebody could just describe this completely for you. So the surface under has this friction constant, and then the force that you're using here is that, and then the angle of the pole is this, and then the angular velocity is that, and the velocity of the cart is that. So you can write down a bunch of physical parameters, and once you know all of those physical parameters, then you can say if you push it right or left, what's going to happen, right? And once you know those physical parameters, you don't really need to know what was the physical parameters at the very beginning of time, right? So you only need to know what is the physical parameters right now to be able to write down the dynamics of the problem for the next time interval. Everybody's clear? Everybody's cool? So here again, the state that you have, all of those physical parameters, and you can again say that this is a Markov process because every time the next state, the next angle, the next distance, the next velocity, everything depends on what had been before plus the force that you have used, right? And the return every time is going to be 1 as long as you're not violating those limits. If you violate the limits, then it's going to be 0, right? And you again want to maximize your reward. You want to keep playing as much as you could, meaning each time you want to get reward 1, you don't want to fall into reward 0, right? Okay, so that is again kind of RL environment. What is the transition function? Again, as I told you, basically this is solution to the dynamics, right? So you write down the Newton's laws, and then you just find out what is the next angle and what is the next distance, right? So you can say what is the next state, given that you know what is the current state and what is the action that you are doing. And the reward is going to be obvious. I mean, if you say that the next state is going to be the case where you're violating, then the reward is 0. If the next state is supposed to be the one which you're still in the limits, then you are going to get reward 1, right? So this is the reward function. This is the transition function. And you can again see that this is a very hard thing to write, right? Because you need to know exact details of the dynamics, right? Everybody's cool? And we can have even more complicated form of problem, for example, the stock market, right? Something that people are always happy to investigate, but they're going to get disappointed when they do it, right? Because nothing can really describe it. So again, the stock market, the interaction that you are doing with the stock market is going to be formulated, can be formulated in the same framework. So you could say the agent is the guy who is trying to buy or sell, right? So in a very simple form, it has two actions, buy, sell, right? So it has two different actions that you can do every single time. Then the environment is eventually the market, maybe lots of other information with it, right? The soft information that could impact the market. It's hard to explain what is exactly the environment in this case, but you can think of anything impacting the prices, right? So that is the environment, and then you can say the state is any piece of information which can evaluate the price, right? Well, this is very abstract kind of describing it. In practice, what is that state exactly? If we could have known, then people would have been rich. Nobody would sit here. We just were doing our trades. But the problem is that you don't know really, right? But you can always think that state exists, right? You don't have access to. But anything that is going to impact the market is going to be inside this state, right? And then you would say, okay, each time that I'm in one particular state, then the environment, is in one particular state, I'm going to do one action. So the agent could buy or sell, and by doing that, you're impacting the environment, right? Maybe the price goes up or down, right? And there are also some other bunch of parameters there to impact the market. But at the end of the day, the state is going to change from one point to another, right? And the reward function is again the kind of profit you make out of that particular action, right? So obviously here, this is not even that easy to imagine what that thing is, but you can abstractly think about that, right? Whereas in the physical case, the card pull, you could imagine it, right? You could say that there are dynamics. It's too messy to solve, right? In the very first one, in Tic-Tac-Toe, you could simply write it down, right? Because it's a very simple game. Everybody's clear?